So hello, welcome to the EVAC General Assembly meeting for April 15th, 2022. If you attended the meeting live, this doesn't look like what was happening during the meeting because we had some technical difficulties and we had some issues with starting the recording. So what we're going to do is re-record the intro part of this. Tom will explain about the small gap in our guest, Dr. Jenny Patience, talk. And so we hope that you enjoy this Zoom recorded meeting, and welcome. We're glad that you're joining us for this, and that we hope that you find the Zoom presentations from EVAC meaningful and useful to you. The agenda tonight is general welcome. We'll do some introductions of our officers and board. We'll talk a little bit about our current business, and then our featured speaker is Dr. Jenny Patience from ASU. Starting out, this is just a photo of a beautiful nebula from Bernard Miller, one of our members, and it's a background for our officers and board. I'm Claude Haynes, the president. We still have an opening for vice president, and we would really appreciate it if one of you would volunteer. Tom Mosden has been helping greatly to fill in that position and help us get speakers and do technology, but vice president would be helpful. Gordon Rosner is the secretary. Our treasurer is Alexandra Nachman. And the board, Dave Kosho, John Kester, Bill Peters, Brooke Schofield, and Derek Youngson, have worked hard to try to keep the club going, even during this time of pandemonium. Also, James Yoder, our property director. Alexandra also serves as our events coordinator, and then Artie Pazanka, webmaster and newsletter editor. Our major announcement, I guess, would be coming for the May EVAC meeting, which is we're going to go live at the Southeast Regional Library. That would be at 7:30 on May 20th is our next scheduled meeting on the third Friday of the month. Southeast Regional Library is where we have been meeting for years at the corner of Greenfield and Guadalupe. Information is on the website concerning the location and other information. Again, starts at 7:30 the third Friday of the month. There are some things that we would want you to consider. We are requesting masks. If you feel uncomfortable without the mask, that's fine. You have a choice. We're not requiring it, but we do request it. We will space the seating out. Feel free to move the chairs next to people that you are comfortable sitting with. But if you want to be kind of separated out, that's your choice as well. We aren't going to have refreshments so that we don't queue up and stand in a line next to each other. We will simulcast via Zoom. So the library has invested in some technology. Tom and I have been testing it out, and hopefully we'll have a good experience for you with the simulcast via Zoom at the same time. The live meeting may be canceled at the decision of the board if the case count grows and we have a sudden surge, or if we have some really serious technical problems that come up where it's not going to be a good experience for you. But we are going to start with live meetings beginning in May. You will also have the chance to watch those simulcast via Zoom. So if you don't feel comfortable, or if it's more convenient for you to attend that way, we have made a commitment that we will continue doing live meetings and simulcast with Zoom at least through the end of the year. So we'll make a determination as to what the best policy is later on. But for right now, we want you to feel safe, and we want you to be able to attend the meeting in the best form that you feel comfortable with. So for that reason, if you want to attend live, that's great. If not, if you want to watch via Zoom, that's great also. Would like to encourage you to pay your dues if you have not. There are continuing expenses for the club, insurance, things of that sort, the web presence, all of those bills continue to come in. And so we would appreciate if you would pay your bills. You have a chance to do that in May in person. So we hope to hear from you at that time. We really appreciate your support. This isn't a nag. It's just that we're just making a point to say that it would be helpful if we have more people who have renewed their membership. A few things coming up. If you are going to view the partial solar eclipse on April 30th. You would have gotten your tickets already. It's a partial eclipse. It's mostly in the Pacific Ocean down near Antarctica. It will end up in Chile. But we do have a lunar eclipse coming up on May 15th. That's a Sunday evening. It will have already started at when the moon rises about 7:15. Maximum coverage is about 9:11. So we will stay open till about 10 when the park officially closes. The observatory will be open, and we will be asking for some volunteers to help donate some telescopes to look through to look at the moon, because it's going to be low and below 15 degrees. We can't really see through the concrete wall of the observatory. So it will be a volunteer activity night as well. And we encourage you to come out and see it, or to view it with your family, even if you're doing it at home. It's kind of fun. We have a couple of these every year, and this one should be a nice, long, and pretty spectacular one. So at this point, I'm going to turn it over to Tom Mosden, who is going to be introducing our speaker, Dr. Jenny Patience from ASU. We'll be talking about exoplanets. So Tom, over to you.
Thank you, Claude. It's my pleasure to introduce Professor Jenny Patience. She's an astrophysicist at ASU who uses large ground-based and space-based telescopes to investigate a range of topics in star and planet formation. In exoplanet research, her work focuses on the detection and atmospheric characterization of young giant planets and brown dwarfs. She also studies the disks around young stars and brown dwarfs with infrared imaging and millimeter interferometry. In addition to astronomical research projects, she is involved in innovative teaching and research experience programs for undergraduate students from all backgrounds. So it's my pleasure to welcome Professor Jenny Patience. And as mentioned earlier, we will join Jenny's talk about 4 minutes into her lecture. Thank you.
But if we take a spectrum of the star, which is simulated in the cartoon there, then you notice that the lines of the star, so the absorption lines that are present due to the gases in the star atmosphere, those are moving as the star moves due to this orbital motion of the low mass companion. And so with this measurement, it's possible to indirectly infer that there's another object, in this case, low mass and planetary in mass, in orbit about that star. So that radial velocity or wobble technique is one way that we can indirectly discover exoplanets. And next, we're traveling out to another nearby star that is a demonstration of another indirect approach that we can use to discover exoplanets. So in this case, we're going to visit a star that has in orbit another very close planet. And so with this, we'll see an example of the transit method. So again, we have our little simulated planet. And in this case, the orientation of our observatory towards this star, HD 209, is such that the planet crosses in front of the face of the star. And when that happens, you can see that the star is slightly dimmer due to the fact that the planet has blocked some of the light from the star. So what you're seeing in this simulated curve here is the brightness we would measure. And then if you watch carefully, that brightness is steady from the star until the planet moves in its orbital orientation such that it crosses in front of the star. And then we see another dip. And what observatories do is to monitor stars so that you can catch multiple of these brightness dips. And from the time it takes from one dip to the next, that gives us the period of the planet's orbit. And then from the depth of the brightness drop, that tells us about the size. So next you're seeing a simulation of the approach that my students and I take, where this is giving you a simulation of a standard image from astronomy. Now, if you're able to use an advanced technology called adaptive optics that I'll describe, you can focus the light into a much smaller central size. Then if you go further and block the starlight with an opaque mask, then that helps to bring out what you're seeing, those faint points of light. Those are the simulated planets. And so what we'll do here is we'll take now a virtual visit to one of the Systems 51 Eri that was discovered using this approach. And the star had been known to have these rings of dusty material. And so what we found is that we were able to image a giant planet, and its orbital location is such that it's in between the two rings of dusty material. And you're seeing now the actual research images where the starlight was blocked, and then you see the faint points of light from the detection of this young Jupiter. Okay, so I think that's about all we have for the techniques. And what you're seeing now is a view of an example of if you were to look out into the nearby location, how many of the nearby stars would be known to have exoplanets? They've been colored. And so if we then zoom out to a larger view of our galaxy, you see that, green is indicating transit systems. And you see that there's this particular direction along the galaxy that we're able to have discovered exoplanets to much larger distances. And that is due to a satellite that was launched called the Kepler satellite that stared at a particular location in the sky in the direction where you're seeing all those detections. And so in that one direction, we were able to discover many more exoplanets, and hopefully this simulated view here gives you a sense of just how many more exoplanets are out there to discover. Imagine if we could survey our entire galaxy. All right, so I'll go ahead now and give you a sense of what population of exoplanets was discovered through these various techniques. Go ahead and show the next slide here. So again, I'll just start with a comparison of our own solar system so that we can have a comparison point. So what you see down here is the Earth. We're making a plot of the mass of the planet as a function of that orbital distance in units that you can see are tailored to the Earth. So 1 astronomical unit being the distance from the Earth to the sun. So the line here is indicating Mercury's orbit, where this is the closest planet in our own solar system. We think of Mercury as this really roasted world, and we'll see how the exoplanets compare. And then beyond the terrestrial planets are the gas giant planets, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. So if we look at the first exoplanet that was discovered, it was discovered by a technique that actually didn't make it into our video tutorial from the planetarium system we have at Arizona State. It was actually discovered through radio astronomy. And what you're seeing here is an image in the corner of the telescope that sadly is no longer operational, but this is a large radio telescope built into a sinkhole in Puerto Rico. And there are stars that are the remnants of supernova explosions called neutron stars. And they are incredibly compact, only about the size of Phoenix, and having masses greater than the mass of the sun. So these pulsars have very intense magnetic fields. That's what this cone in the cartoon is meant to be indicating. And these rotate very rapidly. So with the radio telescope, what is detected is a signal that varies in time. And the variations are incredibly regular. And so if they arrive early or late, and more importantly, if they arrive in this pattern of early, late, then from that, it's possible to infer that there are planets in orbit about this pulsar, or planet mass objects. And this is very analogous to what you saw in the simulation of the radial velocity wobble method. So what you see here in these blue squares are examples of the planets that have been detected around pulsars. And some of them, in fact, are so low mass that I didn't put them on the plot because they would have skewed the entire scale to be very low. Okay, so the next detection that came in terms of like chronological order, the next way that a planet was detected around a normal star, the first detection of that type of star, was through that radial velocity wobble method that was in the simulation. And so what you're seeing here is a cartoon of the star in orbit about the center of mass. And then you see out here the unseen planet. The spectrum from the star is getting blue shifted and red shifted in this repeating pattern. And what you see down here is the actual data of the first exoplanet detected around a normal star, 51 Peg. You're seeing the velocity of the star shifting up and down and up in this really regular way. And so this discovery was awarded in the past few years the Nobel Prize, because it was such an important discovery in the field of science overall. And so this was the first example. And then what you're seeing in these green points is a population of exoplanets that have been discovered through radio velocity. And you can see that while we grow up thinking of Mercury as this really hot orbital location, many of these radio velocity exoplanets are well interior to the orbit of Mercury. And so these are incredibly hot, highly irradiated planets very close to their host stars. Okay, so the next approach that we saw in that simulation was the transit approach. And so this is the telescope I was describing, Kepler, that stared into a particular field of view. So it was a location in, since you are all probably very familiar with the constellations, so the Kepler telescope stared into a region in the constellation of Cygnus. And the idea was to take images for years in this same field of view, because then it would be possible to search for these transit events. And then the long time baseline was required to be able to search for periods that were longer and longer. So what you're seeing in this cartoon is an example of how the size of the planet, so here's a smaller planet, larger and larger still, is creating a larger drop in brightness as the planet radius grows. So with these transit measurements, we're able to learn quite a lot about the planetary systems, both the orbit from the time between the dips, and something about the size of the planet from the just how much the brightness drops. So then in the pink points on our population study plot here, you're seeing examples where, again, there are a lot of very close orbit systems detected through this transit technique. And so as we started to explore the exoplanet population, we're finding objects that are very different from anything in our own solar system. Remember, this is Jupiter. And so with transits, it was some of the early discoveries were these Jupiter or even more massive than Jupiter planets orbiting well inside the orbit of Mercury, in often with periods of only days. And then as the technique has matured, it's been possible to search for lower and lower mass planets. And you can see it's approaching then the Earth-sized planets with this approach. Okay, so another technique that wasn't in the simulation, but is another way that planets can be discovered. So planets can be discovered by what is called gravitational microlensing. So if we observe a field of stars, so if from the observatory we're looking out onto this distant field of stars, which would remain basically fixed, if a star passes between the observatory and that background star, and it happens to have a planet, then the star itself will cause this brightening. And this is due to the fact that what you're seeing here, these rays of light coming out from the background star are being bent due to the fact that this is a general relativistic effect, that the star will bend the space around it. And then that causes an effect like a lens, where a lens will bend light rays. And in this case, it's not an actual physical optical lens, it's a gravitational warping of the space that's causing the light rays to be bent and therefore brighten. What you're measuring here, it's the brightness not of the star itself, but of the background star. So the background star brightness will peak due to this effect. And then if there's additionally a planet, then there will be extra peaks in these measurements. So this gravitational microlensing, what you see here, the light blue points, gives an indication of some of the exoplanets that have been discovered through this technique. So this technique can discover planets, and one complication is that this perfect alignment that's required for the detection does not recur. So one drawback is that it's not possible to then go back and characterize the properties of these planets, but it's very important for population statistics. Okay, and so then finally, and this is going in chronological order, so this was the one of the later techniques that was able to discover exoplanets, is the one that I'll be telling you more about some of our research results, is direct imaging. So this is where, with a large diameter telescope, it's possible to image directly the photons of the planet in orbit around its host star. And so on these images, now you're seeing actual images, not depictions with schematics. So what you're seeing here is the first case of an imaged planet around a host object. And I say host object, not host star, because in this case, the primary is itself a brown dwarf. And so that made it easier to detect something that was planetary in mass, because the difference in brightness between a brown dwarf, and so in this case, the brown dwarf is thought to be something like 20 to 25 times the mass of Jupiter. So the difference in the brightness of that object to the what's believed to be about 5 Jupiter mass companion, that brightness ratio is not nearly as high as when the primary is a star. Okay, so then the next two images, this was a really exciting time in that the two discoveries were announced at the same time. So you're seeing two images of stars that are more massive than the sun, around which exoplanets that are thought to be giant planets were imaged. So here you're seeing, again, don't worry about this speckly pattern. This is the residual noise from an imperfect subtraction of the starlight of the host star. So that's what you're seeing here. It's just it's not possible to do an absolutely perfect subtraction. And so you're seeing the remnants of that here. And then these three little points of light, each of them is thought to be a giant Jupiter planet. And so the arrows are indicating the fact that this system has been observed long enough that you can see orbital motion. And so the little arrows are showing that they're all moving in a consistent pattern, like you would expect for a planetary system. And now this image here is taken from so the first two were from ground-based telescopes. And then this third image is from the Hubble Space Telescope. And so with the Hubble Space Telescope, this is one of the nearest stars in the sky. This is Fomalhaut. And so the Hubble Space Telescope has a way of blocking the central starlight. And that's what you're seeing here, this dark shape. It has an unusual shape because it wasn't really designed for this purpose, but it can be used in this way. And around it, you're seeing what was known for quite some time, and part of why the star was imaged. This was the purpose of the observations from the Hubble Space Telescope. It was actually to image this ring of dust. And so in the process of imaging the ring of dust and imaging it at different years, in part to study changes in the pattern of the structure of the dust ring, what you can see in this little inset image is the fact that in 1 year, there was a small point of light here in 2004. And then 2 years later, that little point of light had moved. But the key thing is that it had moved very little, whereas Fomalhaut, being one of the nearest stars in the sky, has a very large proper motion. So if this little point of light had just been a distant background star, it would have moved much, much larger. So there's like no ambiguity that this isn't that this is just a background object. So it has to be associated with the Fomalhaut system to have only this small amount of motion. And so it's thought that this is an indication of the orbital motion of the object in the plane of the disk. Okay, so these are 3 example images. And then what's shown in these points here in the black coloring are systems that have subsequently been imaged. And so you can see with the different colors that each detection technique has a different observational bias in terms of which part of the exoplanet population is most detectable. So for many of the indirect techniques, it's helpful to have a very short orbit. And so that means that it's easier for transits and radial velocity techniques to detect short orbit planets. Whereas if you are trying to separate the light of the star and the planet, then wider orbits are more detectable. And so by combining all the different techniques, it's possible to build up a fuller picture of the exoplanet population. And then I'll describe a little more about this imaged population that was the subject of some of the work that I've been involved in. Okay, so why might we like to make this effort to actually image planets around other stars? Well, some of the scientific questions that we'd like to address, you saw that it's the direct imaging approach is better at detecting wider orbit planets, and that's important for understanding the frequency of planets that are out beyond what is called the snow line. So if you go far enough away from the host star, then you'll reach a point where like ice, the temperature will be too cold, and so you'll have ice in outside this radius, and then you'll have liquid or gaseous water inside. And it's thought that this ice line is quite important in the formation models for how giant planets form. So being able to study this population out here is quite important. And so with direct imaging, it's possible to study something, depending on the distance to the star, something like in the range of a few astronomical units out to hundreds. Okay, and then another thing that we'd like to explore with the observations of exoplanets is to understand how their properties change with the host star mass. So there are more massive bluer stars, larger as well, on down to solar-like stars, and then down to the smallest, faintest M stars. So for the transit and radial velocity technique, those are best suited for the solar type stars, and then they can also operate around the M stars, but the more massive stars are quite difficult for those two techniques because these types of stars don't have many spectral lines for the radial velocity, and they're also intrinsically brighter, which is harder for the transit approach. So with the imaging, it's possible to search for exoplanets around these A-type stars. And another benefit of the A stars is that the lifetime of a star goes down as the mass goes up. And so by studying A stars, it's possible to study younger stars. Okay, and then another really exciting property that one of the things that really drew me into the direct imaging field is that when you have detected directly photons from the exoplanet, that means you can start to explore the atmospheres. And so we can start to learn what the constituents are of these atmospheres of planets around other worlds. And we do that with spectroscopy. Okay, so what you're seeing here are examples of the two main ways in which giant planets are thought to form. So there are two broad categories of models. One is called the core accretion, in which the planets build from smaller particles to larger. So this is an example of a dust grain image. It's thought that these grains can accumulate and then over time build up into what are called planetesimals, then into what are called planetary embryos, something like Mars-sized. Many of these objects would come together to form the core of a giant planet, and then the giant planet would at some point capture the envelope, and that's what you're seeing here in the envelope of the image of Jupiter. An alternative model is that giant planets might form through what is called a gravitational instability. So if a disk around a very young star is massive enough and dense enough, then out of the disk itself can rapidly form what you're seeing, these little condensations. This is from a numerical simulation that's suggesting that early enough it may be possible to form giant planets directly, the gaseous part, and rather than going through this bottom-up process of core accretion. So there are these two broad models, and then you'll see in some slides how they make somewhat different predictions on what the properties of giant planets would be. And so that's part of why we'd like to go out and find them and measure their properties so that we can understand more about these, how the planets might have formed. Okay, so another reason that we'd really like to find systems with giant planets in wide orbits is that it's thought that giant planets in wide orbits can provide something of a shield for impacts to interior terrestrial planets. So an example of this was some of these spectacular images of the Shoemaker-Levy comet impacting on Jupiter. So that's what's shown in the lower left here. And so if you can find systems where there's a wide orbit giant planet, then you might like to spend the super valuable future space Earth imaging telescope time to search for terrestrial planets in that kind of system. Because based on numerical simulations that were called, the overall project was called Jupiter, Friend or Foe, there were dynamical simulations of making artificial planets that have a terrestrial planet and a giant planet, and then studying the rate of impactors on the terrestrial planet. And at least in the numerical simulations, what was found is that the terrestrial planet's interior are overwhelming, or are, you see more often shielding than exterior potential impactors being redirected towards the terrestrial planet. So without the giant planet, the Earth, for example, would have suffered more of these impactor events. Okay, so how do we go about doing this direct imaging? So I've tried to give you some background on why we were really interested in doing this. So then how do you go about it? And some of the technical difficulties are summarized here in this plot, where you're seeing a plot of the luminosity of an object over time. So if we look at stars, these top blue lines, what you see is that stars have a period very early in their history when they're a bit brighter, and then when they contract. But then once they have their fusion, they're really pretty stable brightness over very long periods of time. By comparison, brown dwarfs, these objects that are intermediate between stars and planets, they have a very brief period of burning deuterium, which is this isotope of hydrogen, but that gets exhausted relatively quickly, and then there's no longer an energy source, and so the objects just fade with time. And now for planets, there's never any period of fusion. So they simply start off bright from the heat of their formation, and then just fade with time. So if we think about Jupiter at the age of the solar system, then you can see how much fainter. So this is a log scale. So each little step of like here, for example, -8 to -6, that's a factor of 100. So you can see just how many factors of 100 the Jupiter is in faintness, how much fainter it is than a star. And our sun is not the lowest mass star here. So our sun would be up here. And so imaging a Jupiter around a solar age star, so something like 4.5 gig years, is incredibly difficult. And that's beyond what is currently possible with the technology from these large ground-based telescopes. And so what our project did was, instead of trying to search old stars, what we did was to try to search younger stars. So at this 10 million year, 100 million year range, then the planets are much, much brighter, and then they become possible to image. So that's how we get around the fact that the planets are fading over time. But there's another factor that's really important, and we'd like to image Jupiter-like planets in orbits that are comparable to the outer parts of our own solar system. And that pushes us into a regime where the angle between the star and the planet is very small. And so just to give you an example, so if a star is at 50 parsecs, which is still quite nearby, then the Sun-Neptune distance, so the outer part of our own solar system, would be less than an arc second, so 0.6 arc seconds. And that means that to be able to image that small of an angle, we need to use a technique which is called adaptive optics. So I'll show you that in a moment. Okay, so with the way this works is that there's a system that's able to measure the light coming incident from the star, and then will essentially correct for the effects of the atmosphere. All right, one way to do that is to launch a space telescope so that you go above the Earth's atmosphere, but then you can't launch such a large telescope until quite recently with JWST. So what we did was we have a system where there's a mirror that can deform and correct the Earth's atmosphere, and then you get back the imaging that you would have otherwise. Okay, this is just an overview of the system. I don't think you, if you'd like, you can ask afterwards about the details, but let me get to some of the results we see. I thought you might like to see the telescope that we used was in the southern hemisphere. So what you're seeing here is a little movie of, you see Orion upside down. This is Chile, and you're seeing the I think it's either the Magellanic Cloud or, well, maybe an amateur can correct me if I think that's the case. And so this gives you an example of the skies over the observatory where we were working. And this is the moon being really bright in the sky. Okay, and so then this is now an image to show you what some of the data looks like. This is the starlight blocked off. And then what you're seeing, it looks like the planet is, this is an actual planet being imaged. It's not that the planet is racing about in its orbit. This is due to the fact that it's an LTAS telescope, so the sky will rotate. And that's part of how we distinguish a companion to the star from just this background noise from an imperfect system. Okay, another way we do that is here you're seeing we're stepping through different wavelengths. And in this case, a real object will stay still, and then optical effects will move outwards with wavelength. Okay, and then this just gives you example images. The upper row are the images that were known prior to our study, and then you're seeing now the much higher quality images in this bottom row. And that enables us to do more detailed study of the exoplanets and these disks. Okay, one system was called Beta PIC. And so these are earlier observations, and then are some of the newer observations added on. And so with that, it's possible to map out the orbit of the system. It was possible that this could have been the first imaged and transiting system, but the planet itself didn't quite transit the star. However, its region of gravitational influence did. And so there was a big study at this time of conjunction when the observatories would be looking and seeing this region called the Hill sphere crossing in front of the star, looking for comets, but I don't believe any were actually detected. Okay, another thing we can do with the images of the planets is to break up the light into the spectrum. And so you're seeing examples here of spectra of imaged planets. And then here's another example where when there are multiple planets in the system, then we can start to do comparisons of the different exoplanets. Okay, and then this is the example spectrum from the planet that was newly detected with our large survey. And part of why we were so excited about this planet is that from the spectrum, we see an indication of this absorption due to the presence of methane. And methane is interesting because it only occurs if the temperature is cool enough. And this relates to the how the object might have formed. So the thing that's really interesting is that when we put together the spectrum over many wavelengths and then added in longer wavelength photometry from another observatory, what you can see is that the gray points are the data. That's what my students and I work on. But other faculty and their students work on these red lines, which are theoretical models. And so what you can see is that despite all the work in making these models match the physics of the atmospheres of exoplanets, none of the models could quite match the reality of the data. So this is an example of why we really need more of these measurements to be able to really understand the objects better. Okay, and this is giving you an example of how those two different formation approaches predict different properties over time. And so I'll jump to the data. So this is why we were so interested in the system, the 51 Erie planet, because it's combining all those measurements at different wavelengths. We were able to estimate its luminosity. And given the age of the system, it's the only imaged planet thus far that's potentially consistent with this core accretion model of formation. Whereas the others that have been imaged are high enough luminosity that it's most likely they formed through that collapse model. Okay, and so then this is just giving an overview of some of the image systems. And then when we look at their images, you see that not only planets are visible, but sometimes these disks. And so what I'll show next is we have one little simulation that maybe we can finish up with on visiting the, a little virtual visit, of some of these disk systems. So what you'll see here is first a model of our own solar system, where out beyond Neptune, this is the Kuiper Belt. And so this gives you like a sense of scale for where the dust occurs in our own solar system. And then what we'll do is we'll go ahead, this is that Fomalhaut system where there was the imaged planet I showed earlier. So what we're doing now is having a little zoom out to some of the stars that were observed in this planet and disk imaging survey. And what you see is that we were searching nearby stars within, typically within 500 light years. And you'll see images pop up. So we surveyed about 100 stars for disks. The colored points are the stars we observed. You see they're concentrated in the southern hemisphere where the observatory was. And then the ones with this orange color, we have resolved debris disks around them. And so what we'll do next is we'll put the actual research images on top of those locations. And so as we're zooming in, what you're seeing is the research data of the arc of the rings of material. And then the exact shape of what we see depends somewhat on our orientation. So here's an example where we have a more face-on view. And then part of what we're studying with this is if the rings of dust are not symmetric, then that can tell us that there's an indication of some kind of gravitational disturbance. And so that can give us an indication that there are planets present, sometimes even planets that might be too faint to actually image. So we're flying around to see examples of those disks. And then you can be looking for those kind of structures where this is one where now you're seeing an asymmetry and where there's a longer disk on one side than the other. And that's a rare example where there's both an imaged planet and a disk. So we can study possible interactions. And this is now, we'll just end with an overview of many of those structures. And it's thought that these may be examples of what our own solar system might have looked like earlier in its history. So maybe I should stop there so that if there are questions, if anyone would like to ask, then there's time for that.
Okay, thanks, Jenny. It's very interesting. Yeah, in the Q&A, I will try to, I know Tom Curry doesn't have a microphone, but if you have a microphone, I'll unmute you. But Tom Curry asks, were any of the systems you looked at binaries?
So for the way that the imaging system works, there's only one spot, one coronagraph to block the starlight. So within the field of view of the instrument, which is just a few arc seconds, we definitely had to avoid binaries where they would be a visible binary. But some of the systems were close spectroscopic binaries in which the blocking coronagraph could cover up both stars, or a few cases had much wider companions. So the companion star was outside the field of view. But actually that was part of what my students and I worked on. We had to do a precursor survey to find all the binaries that would be within the field of view. So one of my students did a thesis on binary stars preparing for the planet search.
All right. queue up your questions. While you're thinking of them, I'll ask one question. So what is the main thrust of studies now? Is it finding more planets, or is it focusing on one particular aspect?
Yeah, I think that there's a combination. So there are programs that are searching for new exoplanets always. And so an example of a space mission that is dedicated to searching for planets is the TESS mission. So that's the Transiting Exoplanet System Satellite, I believe. And so that's an example of a search program. There are also ongoing imaging radio velocity searches, but I would say a big thrust now is in the characterization of the systems. So that can take the form of characterization of the atmospheres, understanding what the compositions are. It can also take the form of the understanding the dynamics of the planetary systems. For example, when there are planets and disks, or when there are multiple planet systems, or planets in binaries like the previous question. So those would be examples. I think characterization is really one of the real frontier areas of exoplanet research now.
Okay, thanks. Derek, you're live.
Yes, thanks, Tom. Hi, Jenny. Thank you. Excellent presentation. Very interesting. Question: will the JWST be able to add to this this effort in detecting exoplanets?
Oh, yeah. So JWST, I mean, of course, everyone is so looking forward to using that. And there will be a lot of, I think, really spectacular results coming out from JWST. One area, so since the disks are on the screen here, one thing that JWST can do is get a spectrum of these disk structures. And because it operates in the mid-infrared, JWST covers a wavelength range that's really important for understanding what sort of grains are present in the disks. So different materials, like even on Earth, can be studied in the lab. You can get a spectrum, and then you would be able to determine what types of dust grains are present in the disks. So that's like an example on the disk side. And then for the exoplanet, similarly, that large and different wavelength range of the mid-infrared in particular will be really important for understanding what the composition of the exoplanet atmospheres is. So I think there'll be a lot of, I mean, there were, I think it's something like 20 to 25% of the time of JWST is dedicated for exoplanet research.
Oh, that's great.
On,
so there was time
yeah.
allocated. That's excellent.
Oh, yeah, exactly. It's there was a panel that reviewed telescope proposals that far exceeded the amount of time available. So so many astronomers wanted to use JWST, and through this competition, quite a bit of time was allocated to exoplanets. Yeah, so yeah, I think you can look forward to many really interesting results.
Excellent, thank you.
Okay, and Tom Curry has another question. Was there any statistical information that would let you generalize that there will be X number of systems with only large planets, no rocky near sun planets, or that all systems will be similar to our solar system?
Oh, so, okay, yeah.
Yeah.
So that's a question that, yeah, let's see, I'm not sure if I should go all the way back to the population slides, but that's something that finding like a true analog to the solar system, that is still something that I would say it's fair to say we would still be looking for. That none of the exoplanet systems that have been detected thus far are like exact analogs, in part because it's very difficult to know about both terrestrial planets in terrestrial orbits, like Earth-like planets in Earth-like orbits. That's like right at the boundary of what's detectable. And then Jupiter mass planets at Jupiter orbits, that's also difficult. So the field is very much working towards that. But for example, it's easier to detect something like an Earth size planet in a closer orbit. So finding the perfect twin to the solar system, that is still, I think, in the works. People are still searching for that.
Okay, thanks. Steve, your microphone is live. You can go ahead and ask your question.
Thank you. Hello, Professor. I just wanted to, I apologize if I missed this during your lecture, but I just wanted to ask, how do you verify you are observing is a planet and not a brown dwarf in orbit?
Yeah, exactly. So that goes back to, let's see, I might be able to go back to some of that goes back a bit to the spectroscopy. And so from the spectrum, let's see, this one might be better. You measure a certain brightness, and then you know how bright the star is. So you can calibrate the brightness of this object and then also get this spectrum. And so it tells you that the object has a certain luminosity, and then we actually have to rely on these theoretical models here. So the models predict what luminosity an object will have. Here you see the different colors are for different masses. And so it is a bit, there's some debate about where exactly the transition occurs between brown dwarfs and planets. So there are two main ways that have been proposed to distinguish the populations. One is that there's this limit of 13 Jupiter masses below which the object can never have fusion, not even this brief deuterium fusion. So that's one definition that's been used. So anything less than 13 Jupiter masses can get called a planet in that way. Another is to, what you'd really like to know is how the object's formed. Like, did it form in a disk like you might expect for a planet, or did it form collapsing from the cloud like a brown dwarf might form? That's of course harder to know, but that's another way that you'd ideally like to distinguish between planets and brown dwarfs. And then ultimately, I'm glad you asked the question, because now I get a chance to justify going a little tiny bit ahead to my one more slide to show the movies that I had. So with the if you can monitor systems over time, then you can get an actual dynamical mass. So that's what you're seeing here in these movies. This is, if you look here in the corner, you'll see the time marching forward. So you see over time, we can monitor the orbits, and then dynamically, then we can determine the masses. And so once you know the mass of the object, then you can decide which of these divisions between brown dwarfs and planets, which mass division you'd like to use. And decide if it's a brown dwarf or a planet. And then here, since now there's a chance to show more of these movies, here's the beta pic system where it's the planet that was imaged first on one side, and then if you were to follow it in time, it actually popped out into the other side. And then here is the movie. This is now a very large orbital period, so you don't see much motion for the object that was detected at this very wide orbit around Fomalhaut. So yeah, that gives you an example of how you could decide between brown dwarfs and planets through dynamics or through the luminosity and age.
All right, thank you, Professor. Appreciate it.
Those are pretty cool videos, Jenny. Do you have any more you'd like to show?
I know, I'm so glad that you asked a question so I could bring them in. I was afraid of the time. So yeah, okay. I think that's exhausted my video bank between the ways to find planets, the visit to the disks, and then these orbit movies. Yeah.
Okay, so great question. And I guess looking to the future, there's a proposal for a exoplanet hunting dedicated telescope, right? I don't know if you want to say any words about that.
Yeah, so there have been two space-based transit search satellites. So the first being Kepler, the second TESS, and those have been quite successful in discovering populations of transiting planets. Kepler stared at a particular point in the sky, and then TESS took the alternative approach in scanning the entire sky, focusing on bright stars. And then, yes, there are various proposals about follow-up missions, and the community recently put out a what's called a decadal report that is designed to give priorities for the upcoming decade of how to allocate astronomy resources. And among the topics that was really heavily discussed would be possible architectures for large missions to search for planets and characterize them through, in this case, so what you're seeing here is a star that's surrounded by giant planets, but there are ideas for missions where you could push down this detection into the terrestrial planet regime. So that's a big jump in technology, and that's why this sort of decade-long plan is something that it would take to have the technology development to be able to think about those kind of projects. So yeah, it's something definitely that the field is really interested in having as a big long-term goal, doing this kind of study, not only restricted to giant planets, but moving into the terrestrial planet regime. And in that case, the planets themselves are not necessarily going to be bright enough to image like their thermal emission like we're doing here. It may be that it's scattered light. So the host star would be illuminating the atmosphere of terrestrial planets. At least that's one approach that's being considered.
Okay, great. Sounds like there's plenty of work for postdocs and grad students, right?
That's right. Yes, it's definitely a field that's always part of what I find so fascinating about the work is that there's always something unexpected, and there are always new discoveries, and there is always more to be pushing towards.
Okay. Oh, I see one more question in the chat. Are there estimates of percent of stars with exoplanets?
Oh, yes, there are. And I'm sorry I don't have the latest number at hand, but it's very large. It's by no means unusual to find a star or to expect that a star has a planetary system. You had a bit of a view of that in our simulated view of the nearby stars, where you saw all those circles of the nearby stars, those that have actually identified planetary systems. And then if you extrapolate from the detections, it's on the order of, oh gosh, I'm sorry I don't have the exact number, but certainly over half have some sort of planet.
Okay. And I think that does it for questions, but our speakers do get a complimentary EVAC polo shirt. And I do want to show the three colors.
Okay, yeah, here, let me do the stop. If
Okay, this is the, that kind of looks bluish, but it's a dark gray. And then this one is a navy blue, or royal blue. And finally, another one is the light gray. So it's hard to.
All right, well, thank you so much. I mean,
Yeah,
certainly
sure.
if you have excess of one color, anything would be wonderful. Thank you.
Okay, no particular color preference. Okay, great. And I did want to share one more thing, our YouTube channel. So I did put the link in the chat. If you did a Google search for YouTube EVAC meetings, you should see something like this with the homepage. And the playlists are by year, 2020, 2021, 2022. 2020, of course, kicking off the pandemic, and under the view full playlist, there they are. They're in order by month. So I just wanted to share that. And if anyone wants a shirt, hopefully we'll bring them to the meeting in May if the meeting is in person. And otherwise, send me an email and I'll put one aside for you. Having said that, thank you very much, Jenny. And back to you, Claude.
Yeah, thank you again, Dr. Patience. That's a really wonderful presentation. We really appreciate it. I apologize again for my technical problems early this evening. It seems my computer has decided to die. I think Tom put a curse on it this morning when we were doing some other work. But I think that's it. We look forward to seeing you next May 20th for an in-person meeting and Zoom meeting at the library. Check the Observer for the details. And with that, I think we're done. So good night. And if you're celebrating a holiday this weekend, or if you're going now to work on your taxes, you gotta hurry.
Okay. All right. Goodbye, everybody. Good evening, I should say.